Okay, so we should wait a few minutes to get the. to make a class. We have two speakers today, Aaron Jackson and Efetov. And the first talk is going to be given by Aaron. Can we maybe dim the lights?
Yeah, they probably have many buttons if you click the right one. Two.
I think.
No.
No, in the other direction.
It's not that they were.
That's a bit too much.
Keep going.
Sorry. No, sorry.
Oh, there's.
Let me see. I'm afraid this is probably what.
I think
Go with it. This is probably
Hello, my name is Aaron Jackson. I'm a postdoc with the Harris Group at Howard University. Today I'm going to present a new project that we just recently developed. So because it's new, we don't have any experimental results to present, but hopefully that will change in the near future. So the overview of this project is that we plan to fabricate a structure in diamond using nitrogen vacancy centers coupled to carbon-13 to demonstrate quantum bit storage. Hopefully this project will lay down the groundwork, and eventually there will be a quantum register developed with this configuration. We're using nitrogen vacancies to set the spin. There's several reasons for that, but the main reason is that the spin state of the nitrogen, the negatively charged nitrogen vacancy is fully addressable. So you can set it with microwaves and read it out optically. So that's very important. Also, the nitrogen vacancies have a long coherence time at room temperature. And the problem is with the nitrogen vacancies, you have to be able to control the charge state of the NV centers. And that's something that I'm going to discuss a little bit later. And that's actually one of the main parts of this project. And also the nitrogen vacancy centers need to be close to the surface, about 5 nanometers from the surface. We're using the carbon-13 for the long-term storage. Although nitrogen vacancy centers have long coherence time, the nuclear spin has much longer coherence time. And we're using carbon-13 since carbon-12 doesn't have a net spin, and it won't be able to couple with the nitrogen vacancy centers. So a classical register is a group of N flip-flops that can store 2 to the N possible values. The bits are represented by voltage, 0 for logic level 0, 3.3 volts or 5 volts for logic level 1. The register stores one value at any given moment. For a quantum register, it's a collection of quantum bits, and in this case, it's a vacancy center coupled to carbon-13. The bits are represented by spin. Now, the interesting thing about these quantum registers is that they store all possible values simultaneously, which is a unique property, which also gives quantum computing the ability to solve problems that can't be or are not feasible with classical computational methods. So quantum registers are a basic building block required for quantum computers. So that's why we're interested in studying this. So this is the proposed structure. It entails nitrogen vacancy centers within a carbon-13 layer. And these are going to be 5 nanometers from the surface. Of course, this is not to scale. And if they're close to the surface, we can couple them with waveguides and cavities if that's something that we want to do. But this green area here is this hydrogen termination for the diamond, and this is aluminum Schottky contact. So with the combination of these two, we can actually deterministically control the charge state. So that was demonstrated by another group in Germany. So because we can deterministically control the charge state of these nitrogen vacancy centers, we can study the neutral vacancy and the negative charge vacancy. So it's actually been proposed that the neutral charge vacancy has an even more sensitive magnetic detector than the negative charge density. So it'd be interesting if we could actually get some data that supports that hypothesis. So nitrogen vacancies are basically a nitrogen impurity substitutional impurity next to a carbon vacancy along the 111 direction. So there are 4 unbonded electrons associated with that vacancy, plus 1 from the nitrogen valence. So a neutral charged nitrogen vacancy has 5 electrons and has a total spin of a net spin of 1/2 and a 0 phonon line at 575 nanometers. If that vacancy acquires an electron, it transitions to a negative charge state. And that has a net spin of 1 and a 0 phonon line at 637 nanometers. If the neutral vacancy center loses an electron, it becomes positively charged. That has no net spin and it does not have any fluorescence, so it's not very useful at all. But the whoops, sorry. But the the neutral NV center and the negatively charged NV center have net spin, so they can couple to the carbon-13. All right. So there's some challenges when using these nitrogen vacancy centers. One is we want them to maintain their charge state, but unfortunately they stochastically change between neutrally charged and negatively charged. Also, the location of the vacancy center affects the charge state as well as the surface termination. We also want long coherence times for the spin states. So we want the minimal amount of crystal imperfections as possible. So really the nitrogen has to be incorporated during growth. You can implant the nitrogen, but the implant causes damage to the lattice, which decreases the coherence time. So this shows you the basic energy levels with respect to the band of a diamond. So the neutral vacancy center has a ground state about 1.2 eV above the valence band, and the negative, I keep doing that, and the negatively charged vacancy center has a ground state about 2.94 eV above the valence band. So the position of the Fermi level determines what charge state the vacancy center takes on. So if the Fermi level is below this level here, it's going to be, the vacancy center will be in the positively charged state. If the Fermi level is between 1.2 and 2.94 eV, the vacancy center will be in the neutral charge state. And if the Fermi level is above 2.94 eV, then it will be in the negatively charged state. So the key to be able to control the charge state of the nitrogen vacancies is to be able to control the position of the Fermi energy. And that is done with using the hydrogen termination as part of it. So the hydrogen terminated diamond has negative electron affinity. So moisture from the air is attracted to the surface, and then the electrons at the surface of the diamond are trapped at the interface between the water and the diamond. And that causes, oops, I keep doing that. And that causes a 2D whole gas to be formed in this area here, and that's within about 5 nanometers of the surface. So any vacancy center located in this area is going to be in the positive charge state because the Fermi energy is going to be below the the valence band. So the other part of controlling the charge state is getting an aluminum Schottky contact to the surface. So if you evaporate aluminum contact to the surface, you develop it becomes a Schottky contact, and there's a 1.13 eV barrier height. And there's a depletion region that forms underneath the contact. Sure.
And say germanium or silicon, they actually grow out in the hydrogen atmosphere because
Well, I'm not familiar with that, but certainly when you grow the diamond, it has to be in a hydrogen atmosphere. So usually with the hot filament reactor that we have, we flow in about 80 to 1 hydrogen versus methane. But I'm not sure exactly, I mean, other than etching away the non-diamond carbon, I'm not sure what other benefits the hydrogen provides.
You know, just neutralize perhaps if you don't want to see it. I mean, whatever it might be. Yeah, okay.
Okay. So again, the so if the NV centers are in this region here, they're in the positive charge state. So now, if you apply a voltage to this aluminum contact, you start to raise this Fermi energy up. And at about 10 volts, the Fermi energy is higher than the 1.2 EV. So then the vacancy center transitions from the positive charge state to the neutral charge state. And if you increase the voltage to about 20 volts, then you get the transition from the neutral charge state to the negative charge state. So you can, at this point, you can deterministically set the charge state of the NV center. So now I'm going to talk about the growth of the structure. So we're going to start off with a single crystal diamond substrate and do some surface smoothing, similar to what the Lonkar group does, which involves mechanically polishing the diamond and then dry etching. After doing that, you can get RMS roughness of less than 1 nanometer. On top of that, grow a buffer layer. And the buffer layer just needs to be thick enough so that we're isolating the active area from the substrate. And I'm assuming that the CVD diamond that we grow is of higher quality than the substrate. And then we grow on top of that the nitrogen doped carbon-13 layer. So it needs to be around the order of 2 nanometers in thickness. So that's going to require growing at a very slow rate. Typically we grow about 100 nanometers per hour, which if you want to grow a 2 nanometer thick layer, that's about 1 minute of growth time. So that's not something that you can really repeatably do. So we're going to have to at least find a way to drop that growth rate to about 10 nanometers per hour at the very least.
What's the density of nitrogen?
Well, obviously that depends on the amount that we introduce into the chamber, but we really want to, for this, we want to keep it around 10 to the 12 per centimeters cubed. But we might need to do some in situ etching if we can't get this growth properly calibrated. So we can overgrow and then etch back, and it's easy enough to do the in situ etching because we can just introduce a oxygen plasma into the growth chamber. And then on top of that, we put a cap layer, and that needs to be about the same order of thickness, about 2 nanometers, and that's to make sure that we want to ensure that the nitrogen vacancy centers stay within that 5 nanometer range from the surface so that they're in that 2D whole gas. And then the fabrication, basically the steps include just first finding the NV centers. Now, a lot of people irradiate their samples with electrons to generate vacancies, but we've observed formation of vacancy centers during CVD growth. So I don't think that we're going to need to do that step. I think we'll be able to get the density of NV centers just from the CVD growth alone.
Do you know how local vacancy is, just a pure vacancy?
Right, the vacancies definitely are mobile, but you have to heat them up to about 800 C. Start moving around. But I mean, that's how they generate these nitrogen vacancies for most people. They implant in the nitrogen, and then they anneal the sample, and the vacancies move and attach to the nitrogen.
Once it's taken the nitrogen,
Right. Unless you heat it back up to 800 degrees. So we locate the NV center, and that's typically done with just a confocal microscope. And then once we locate the NV center, we fabricate around the NV center. But we need to get the hydrogen termination first. Now we have to locate the NV center before we do the hydrogen termination, because the hydrogen termination will put the NV center into the positive charge state, which has no fluorescence, so we wouldn't be able to see it otherwise. And then evaporated aluminum contact, and we have to make sure that the vacancy center is within a micron of the contact edge. Otherwise, it won't be in the depletion region of the contact. And we won't be able to control the charge state. And then evaporated aluminum contact, an ohmic aluminum contact, mask off the active area, and then use an oxygen plasma to isolate the device. So in summary, we're trying to make a structure that can be used for, potentially used for a quantum register. So when it's all fabricated, the NV center should be in a known charge state. If there's no voltage on the contacts, it should be in the positive charge state. As you increase the voltage on the contacts, it will transition from positive charge state to neutral charge state to the negative charge state. And then the NV centers will be coupled to carbon-13 for quantum bit storage. And we have the ability to set and reset the spin state of the NV center and the carbon-13 nuclear spin. So there's some references and acknowledgements, including the grant number.
No, I'm asking if there are any questions. Yeah.
When you're drawing these, they come out polycrystalline. Of course, it'd be lovely to have it be two-dimensional. But rather than do that as being bad, I wonder, can you like seed it with little bits of diamond and then grow golf balls of diamond that don't touch each other, and then make each one have an NV center in it?
Well,
okay.
Well, that's actually something that we're actually pursuing over at Brookhaven, but not related to this. With this, we're going to try to start off with a single crystal substrate, so when we do the CVD growth, it will be single crystal on top. But that's an idea that we're actually pursuing in another project.
Because NV is really small, so the sample doesn't have to be huge.
Right. Yeah. Well, we just have inputs for the gas lines, so we can hook up an oxygen tank, and then there's a DC power source in there, so it generates a plasma. No, actually, I've read some papers where oxygen actually helps smooth out the diamond growth. So, but I don't have any experience with that, so I'd have to actually test that. But the one thing we certainly want to be careful of is we use a lot of hydrogen during the growth, and if there's oxygen, we don't want to have a reaction. Yeah.
Are there any more questions? Okay, so let's thank Aaron again.
Thank you.
And there's a lot of pizza, so if you want to grab
Yeah, thanks.
third slice, that's
Probably
okay.
don't need that, right?
Yeah, we do.
Yeah, I need it for. Okay, all right. Oh, it's for the. Oh, that's right.
Just for the video.
Okay. 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 All right.
It's off the screen.
So I have to push this thing over
Where is your mouse? Oh, there.
there. There it is. Okay. All right. So,
Okay, so our next speaker is Dmitri Efetov, still at MIT, but I believe soon to move to sunnier
did you
lands.
see the weather here?
He's going to tell us about what the quantum limit in graphene.
Yeah, thanks a lot, Pablo, for the invitation. And actually, I had the Friday 8 o'clock morning session at APS, so actually this audience is much bigger than at APS meeting. So,
Okay.
so it's not a problem. Right, so I'm going to tell some work which we're trying to wrap up at MIT. So there are several papers which we just submitted and which are going to come out soon. And basically, we try to explore the quantum limit of graphene photodetectors. And just to give you, so this is our team. So this is basically work which was done in, mostly in Dirk Engel's group, but we also collaborated with Philip, who provided some of the devices. Also, Jim Hone provided some of the devices to us. And mainly, this project was also driven by Kinshon Fong, who's at BBN Raytheon. So just to give you some very, very, very rough overview of graphene photodetectors. So graphene photodetectors were around for several years now. And basically, they excited a lot of interest, basically because of their ultra-broadband absorption properties. So basically, since graphene doesn't have a band gap, and is basically a perfect semi-metal, you can absorb light from all the frequencies from the UV to gigahertz. This makes it, in particular, interesting material for example, terahertz application, where a lot of photo detection and optoelectronic devices are pretty bad at this point. And here, the first paper was probably done by Pablo in 2011, where they observed the photothermoelectric effect in graphene. The second most important thing, I think, is ultra fast. So here in Frank Kopen's group at ICFO, people measured that, graphene electrons respond to light on a femtosecond scale. So the typical relaxation times are in the order of 50 femtoseconds. And of course, this is probably a selling point, in particular from Dirk's group, in which I am right now, is that you can integrate graphene very easily with silicon photonics. So basically, it's very easy just to prepare a graphene photodetector on a silicon waveguide platform. And the detectors you find, the best graphene detectors at this point are as fast and as responsive as the germanium detectors, which are right now sort of the typical detectors used in this kind of platforms. So one thing I have to say is that all of those mentioned detectors, they operate on the principle of photothermoelectric effect, which was worked out by Pablo a couple of years ago. And in principle, this is so far the most dominant effect, which from the all possible effects you can observe in graphene. But I think one of the drawbacks here is that the sensitivities and the noise equivalent powers which you get from those detectors are rather low. So basically, if you want to push those detectors towards the quantum limit, if you really want to detect a single photon, then probably a photothermoelectric effect is not the way to go. And I will the rest of my talk is basically going to be about the bolometric effect in graphene. So, and of course, the interest of single photon detectors in graphene is there are many different predictions. So, for example, in the terahertz ranges, you could use graphene as for radio astronomy, for particle physics, and of course, there are also applications for thermal infrared cameras. So, what makes graphene a promising single photon detector? So, first of all, graphene is ultra small. So basically, if you think about it, then a typical graphene device is roughly 1 by 1 micron size, and you can almost count the atoms in this material. So basically, 1 by 1 micron graphene sheet has 10 to the 7 atoms. So it's a very small thermal mass if you compare to other bulkier three-dimensional materials. The second thing is that in the ultra clean devices these days, you can actually tune the Fermi energy almost to the charge neutrality point. So you can achieve carrier populations of less than 1 electron per micrometer squared at the charge neutrality point in the cleanest devices right now. So that together gives you a record low electronic heat capacity. So basically, if you want to absorb heat in graphene, then this is the heat capacity you get. It's only 10 kb over micrometer squared. And this is, in my best of knowledge, this is like the smallest heat capacity, electronic heat capacity. Electrons, exactly. Without the lattice, exactly, yeah. And then this brings me exactly to the second point, is that the other advantage of graphene is that the electron phonon relaxation time is extremely weak. So if you want, so the electrons, once they reach a certain temperature above the lattice temperature, their relaxation is very slow. So the electronic and phononic temperatures become decoupled, and the relaxation back to the phonon temperature is very slow. And this is basically given, again, by the small Fermi energy, where the only cooling pathway is electron acoustic phonon cooling. But also the electron-electron interaction time is super fast. So if you heat up one electron, it equilibrates with the Fermi surface very quickly in 50 seconds. But then it decays to the phonon lattice at low temperatures in nanosecond time scale. So the electronic temperature remains hot for a very long time. And this is, again, is the second argument, is that we have a record low thermal conductivity between electrons and phonons, which can be as low as picowatts per Kelvin per micrometer squared. So what we did recently, so we just submitted a paper to PRX where we did all those calculations. And basically, we find out that if you take 1 micrometer squared graphene device and you look at the electron temperature increase as a function of for a single photon. So if we absorb a single photon in graphene, how much does the temperature increase? So if we start at 3 Kelvin, then for near IR photon, the temperature can increase up to 20 Kelvin at low densities. So it's a huge temperature increase which we can achieve with just one single photon. So if we now can find a way to properly detect quick rise in electronic temperature, if we can measure the electronic temperature separately and fast, then we think we can, this is a very promising direction to observe this type of effect. So, and this brings us to the bolometric electron principle. So basically, we're looking at the heat absorbed in the graphene and what temperature rise this goes along with. So basically, we can use this simple scheme where the graphene is the thermal mass and the absorber at the same time. It can absorb radiation, and it's only weakly coupled to thermal BEV, which is given by the electron-phonon interaction. And basically, just by the incident power versus the thermal conductivity, we can get the increase in electronic temperature, and the time scales are given by tau, which is equal the heat capacity over the thermal conductivity here. So how do we now measure? So basically, in this picture, how do we get this thermometry right? So yeah. No, because no on substrate, yeah.
But then the model doesn't include thermal conductivity to the substrate, right? Which can be
Exactly. So I mean, our assumption is that the electrons first couple to the phonons in the graphene, and then the phonons in the graphene couple to the silicon phonons, right? And basically, so this would be a second order effect. The phonons of the graphene lattice coupling to the phonons in the lattice of the silicon. So I mean, I will show measurements of the thermal conductivity. So with this technique we're going to show in a second, we can measure the thermal conductivity from the electrons into the surrounding. And we can basically plot out what is the temperature dependence of this relaxation thermal conductivity. And I will come back to this point. And yeah.
electron phonon relaxation time under which conditions? I mean, a nanosecond is a bit, the measurements from machine, etc. show
Right.
more like 10 picosecond.
Yes. Right.
So this is for small temperatures at lower
That's right. Yeah.
small temperature increases at low temperature,
At low temperatures. Yeah.
not the usual optical.
Exactly. And I will quickly go through two sort of different device concepts we're looking at. So the first one will be in steady state. So we're just shining a constant power. So basically, we're shining a constant power. We don't shine like one photon at a time. We just shine a very constant power, and then we can actually work for this relation. We can work out the thermal conductance here, right? So we get the temperature response from the thermometry, and then later on, I will also show detector device which just responds instantly. If it absorbs a photon, it's like a threshold detector. It absorbs, it clicks. Okay. So basically, the way we measure the electronic temperature directly is by Johnson-Noise thermometry. So this is the same way as, for example, people measure the microwave background radiation in space. And the idea is very simple. Johnson-Nyquist noise is basically just thermal noise of the electrons. And the power of this electronic noise is just directly proportional to the electronic temperature. So basically, just by making up a circuit, RF circuit scheme this way, where we have a graphene as a thermal radiator, basically, then we have an LC matching network, which allows us to transmit RF radiation effectively through the wires. And then we amplify this noise, and we just basically measure it with a typical lock-in homodyne detection principle. So, and this type of thermometry was already presented before, again by Casey Funk, who's our collaborator, who's also collaborating with Philip on this hydrodynamic regime. And we can basically use this measurement scheme to map out the temperature of the graphene electrons. Before or after they equilibrate with the lattice, it doesn't matter. It's just like this, the number which we get from here is the electronic temperature. So, and basically, of course, the readout scheme is a little bit more complicated, but the take-home message here is that we get a 1 millikelvin temperature resolution. So we can look at the electronic temperature as it changes like to very small amounts of temperature, so 1 millikelvin. And what I said before is that for a single photon, we actually expect like tens of Kelvin increases. So in principle, this should be a good technique, but I will, yep.
So that's experimental number?
Yeah, exactly, yeah. So basically how we do it is we just sit at a constant temperature, we equilibrate our cryostat, and then we basically look at the statistical deviations of our signal, right? So basically what we do is we do first a calibration. So basically, we look at the Johnson-Noise thermometry as a function of fridge temperature. And then we calibrate, with this linear fit, we calibrate our device. And then later on, if we fix the temperature, we can look at the standard deviation of the signal. And this gives us basically the standard distribution of the signal. And then we can compare it with the temperature, and it corresponds to 1 millikelvin sensitivities. Okay, so since we're talking about optoelectronics experiments, so this is our setup. So we have this whole Johnson-Noise thermometry scheme connected to our graphene device, which is this device here. So basically, we have graphene strips encapsulated in boron nitride, and we have electrodes connected to it, and we measure the Johnson-Noise signal between the electrodes. And all of that sits in an optical cryostat with a confocal setup, so we can basically scan a laser beam around and hit a different spot on the device and heat a different spot at the device. So basically, if we scan the laser along this device, this is the data which we're getting. So basically, we get a strong increase here where the Johnson-Noise thermometry actually happens. So this is effectively our thermometry region. And then, anywhere else in the graphene, if we excite it even a distance away from the thermometry region, we still get a thermal conductivity through, so we get a signal. And also from this measurement, we don't see any signal from the silicon heating up. So I would think if there is like an effect through the silicon, if there's a heating through the silicon into electron lattice, we should see heating like a distance away from it. But but we don't see it right now.
What determines the diameter of the length, rather, in the diagonal of the bright region to the yellow region?
What determines the length here?
Yeah.
Okay.
The whole thing light up if you have the electrons emitting.
Oh, right. So I mean, so basically, what we know is that really the thermometer is really local. So the thermometer is sensitive only to the transport along this small region between the electrodes.
But why?
So we can treat that system as a series of resistors, basically, and it scales. So basically, if there would be a contribution from faraway electrons to the Johnson noise, they would decay as 1 over the width of that device. So basically, we expect the width is here like 2 microns, I think. So 2 microns away, this effect is gone. So whatever heat is, whatever signal we get from a faraway point here is really just the thermal conductivity of the electrons. It's nothing. It's not an artifact. It's really the heat which propagates through the 50 megahertz. Yeah. So we did I don't have it here, but we did we addressed that question. So it's the Johnson noise signal was decaying as 1 over width. So that's why we made our devices like narrow and long, also. Yeah. So what we can do now here with this technique, we can look at the thermal conductivity. As I said before, the thermal conductivity is just given as so the temperature is equal to the power, incident power, and divided by the thermal conductivity. So by recording the temperature and knowing the power, we can deduce the thermal conductivity here. And so this is like a typical data set which we obtain. So we look at thermal conductivity as a function of gate voltage and as a function of temperature. And if I take a line cut anywhere along this line here, we get the following picture. So basically, thermal conductivity first scales linearly with temperature up to a certain elevated temperature at around 100 K. Then it crosses over to a much faster increase here, which approaches T to the 4. And basically, from different relaxation models, we know that the graphene electrons, in principle, are coupled through the Wiedemann-Franz law with electrons everywhere else in the system. So there's heat relaxation between the electrons in the graphene and the leads, for example, which is like an infinite cold reservoir. Also, of course, graphene electrons couple to acoustic phonons, as we knew before, and this is given by this T to the 3rd or T to the 4th power law, where depending on the cleanliness of the device. So, and the Wiedemann-Franz law, so the coupling of the electrons in the graphene to the electrodes follows a linear power law. So basically, from this we can fit our data with those relaxation pathways, and really at low temperatures, we're limited by the Wiedemann-Franz law. So we're limited by the hot electrons diffusing into the leads. So having that information, of course, we can repeat that same measurement with those devices, and basically for different gate voltages and different temperatures, we can retake that map here and look at the cooling length. So additional to the thermal conductivity, we can also compare our models with the decay versus space, right? So and this is what we get. So basically, again, so this is our device, and we basically can take those color maps, those heat maps, as a function of gate, and we can also look at the profile along each line. And what we get is that, first of all, we get a strong increase at the charge neutrality point. And then if we look at the cross-section along the length here as a distance away from the local thermometer, we can get this characteristic exponential decay, which is highly dependent on the gate voltage. So at this point, I'm working actually with Brian in Levitov's group, so we're modeling these results. So in principle, we're hoping also to see some non-trivial cooling mechanisms from this experiment. And also, like what I can show here is that really our temperature of the device as a function of gate scales directly with the resistance of the device. So this again tells us that it's really Wiedemann-Franz law which is limiting the whole heat relaxation process here. So this is right. So this is the typical Dirac peak, and this is our temperature profile, which is overlaying this very well. Talking about Morel lattices in graphene, so we see those side peaks, and there's also increased temperature response in those Morel lattices. So okay, so this is sort of the physical part of the story. So now we try to use this information which we obtained from these measurements to make real devices. So this is sort of the device we made. So since I'm in the engineering department right now, we wanted also to just demonstrate a real device, how this performs. And the device structure here is the following: that we basically took a graphene device and transferred onto a photonic crystal cavity. Because as I said, graphene, one of the bad things about graphene is always that it absorbs only 2% of light. So if you want to make a real life device with graphene, then of course this will be an issue. So any real engineer you talk to and you say it's 2% of light absorption, they think that's the worst material you can make a photodetector of. So to address that issue, we transferred it onto a photonic crystal cavity. And basically, the photonic crystal cavity has a mode inside of it, which basically sends light back and forth 1,000 times. So basically, the interaction between graphene and the absorbed light is dramatically increased. Then we also used the cooling length of the device. So basically, around this photonic crystal cavity, we made the graphene of the same size as we estimated from the cooling length measurements we did before. And of course, we use ultra-clean graphene device because we expect increased enhanced performance at the charge neutrality point. And this is sort of the data we're getting from it. So first of all, if we sweep the wavelength and look at the increased temperature of the device, we can see that for the resonant wavelength, for the wavelength which is resonant with the photonic crystal cavity, we get a dramatic increase of the response. And this increase of the response is linearly polarized. And this polarization, again, comes from the photonic crystal lattice. So if we take, again, the temperature sweep here, then off resonance, we get this signal, and we get a strong enhancement on resonance of the device. And basically, what we can do now is to estimate just how much light are we absorbing here. We can estimate from the coupled mode theory. This is, I'm also not the biggest expert on this, but this is in photonics, people use this. So basically, from the unloaded cavity, we can estimate what is the Q factor of the pure cavity. And then with the graphene transferred on the cavity, we get a loss term. So the graphene absorbs the photons. So we can see that we get the width of this Poisson fit is dramatically changed. So from that difference in the widths, we can estimate how much light graphene absorbs. And we find that in the best devices, we get absorption of almost 92% of light in the cavity. So in principle, this is like this solves the problem instantly of the 2% of light absorption in graphene. And then, of course, we can measure the noise equivalent power. So basically, noise equivalent power is the figure of merit for sensitivity in detectors. So this just tells us how much power we can detect above the noise level. And again, we find power of about 1 picowatt per square root hertz. And in the best devices, it's approaching like femtowatt sensitivities. But to compare it with a single photon detector, of course, this number is not really close. And the reason is that this Johnson noise readout scheme is extremely slow. So for all the data I showed, we did an integration over half a minute. So every data point we integrated for 30 seconds. And even if, and from a single photon click, you expect a signal in the length of picoseconds. So if I integrate one single photon over 30 seconds, then of course, there is, just how slow this detection principle is doesn't allow us to detect a single photon. So what we needed to do is to go get around it. So basically found a scheme where time is not an issue. And what we decided to do is we decided to make a Josephson junction threshold detector. Basically, a detection principle where once you click a single photon, your device is basically switched on. And then unless you switch it off yourself, then it stays there. So there's like no time relaxation process going on. So, and the detection principle is the following. So basically, this doesn't have to be a graphene Josephson detector. So this is just for any JJ. So basically, Josephson junction has a characteristic critical current. And that characteristic critical current is a function of temperature. So basically, if we look at the critical current as a function of temperature here, for example, it decays kind of, I don't know, like 1 over temperature or so. So, and if we take a typical Josephson junction measurement, so basically an IV characteristic, then of course we get this characteristic IV curve where in the supercurrent regime, our current, there's a current even at 0 excitation voltage. So now if we park our excitation voltage somewhere in this ballpark here, and if we absorb a single photon, which brings the critical temperature of the graphene up over the critical temperature of the superconductor, then of course we lose that superconducting current and our device goes into the on state. So, and we can use this principle. Yep.
So if you use the RSA model and you have that tilted,
right.
Well, can you use that language to describe
yeah.
washboard?
Yeah. So exactly. So with the washboard potential, basically your particle is trapped in the washboard potential somewhere, and it has basically a limited probability to tunnel through over this washboard potential. So if we basically bring the temperature up, that washboard potential disappears and the particle slips just through. So basically, the washboard potential disappears because we don't have any supercurrent anymore. We are above the TC. So yeah, so basically we just used that principle that we trapped in this washboard potential. We trap a particle which we assume cannot tunnel through otherwise, and then we just remove the superconductivity at one point, and we get a current through. That's not. So you mean like photo-assisted tunneling type of, like where you photo excited and then it tunnels through? Right. Yes, I think. Yeah. So I think like there's probably many different ways how to make that click. So we just going from that experiment which we talked before, we just assume we heat above the TC and then.
So it's a really tiny.
Right. Yeah. And basically the trick we also use to stay on is we may try to make Josephson junctions which have a what's the name? So basically we try to make Josephson junctions where we try to sweep our bias current to the point where it can go back. So basically there's what's it called? What's the name? Yeah. Hysteresis, yeah, hysteresis is the word, sorry. So we try to make a device with large built-in hysteresis. So once we sit here and we go to the normal state, that device remains in the normal state until we change it. So, but what this allows us to do basically is to sit at this point and to shine light on it and see whether it goes to the normal state and clicks or not. And then what really happens is it does click. So basically, this is the typical data we get. So again, we're just sitting at this in a biased Josephson junction, and we shine light, and then we get those clicks all over the time. And the time scale of those clicks here is a little bit misleading. So this is reset by hand at this point. So we just sit there, we get a click, we count it, we reset by hand.
Can you remind me, so how do you know, how are you sending single photons to the
Through, so we have like a Dilfridge with a laser fiber.
What do you use as a single photon source?
Just an ERR laser. Oh, sorry, we don't have a, we're right now in this stage of the experiment, we just send a very attenuated power. So we just,
But that's not a single photon.
it's not a single photon source, but it's also single photons which are sending it. So basically, if we attenuate the power, that we know, okay, our graphene absorbs maybe like 1 photon per second or 1 photon per minute. We can use just a normal light source and attenuate it long enough, and then we get single photons into the device. So this is not like an NV or a quantum dot which emits a single photon, but the effect in the end for the detector, it's the same. And of course, like, okay, so when we saw those single clicks, of course, like, what do they mean? I mean, we've seen a lot of noise in our experiments.
But the statistical properties of single photon sources and attenuated lasers
Right.
are very different.
Yes. Yes.
The laser is not called a single photon source, so
Yeah. So we're not using.
single photon detector is,
So,
you have to clarify a little bit.
yeah. So we're using just attenuated CW laser source. Yeah. And so so we start thinking, what can we do with those single clicks? So of course, we can look at the rate of those single clicks, how often they occur as a function of laser power. So we can start at really low laser powers. We get a click per hour. And then we can see how many more clicks we get if we increase the laser power. And the interesting thing, which again tells us that it's a single event, is that if we look at the power dependence of the switching rate of this Josephson junction as a function of laser power here, it's linear. So if we increase linearly the amount of photons in, we proportionally increase the amount of clicks. And if we now take a Poisson distribution of those clicks versus time bins, so basically per time bin how many photon clicks we get, they're then just like randomly distributed. So they just follow a Poisson fit. So is this the evidence that it's a single photon detector? No, probably as you say, like I think what the next step would be, we would like to do a Henbury-Brown twist experiment with really single photon sources, etc. So we are not yet, we don't have like a definite proof, but I think we have strong hint that this is likely what's happening in those devices. And I think exactly. So I think we're writing a paper right now, so I think this is going to be questionable first data results, and then then we would like to do a more quantum optics type of experiment. Oh, this is yeah. So this is like, let's say 5 by 5 microns, and the JJ is here. So the gap between the two superconductors is maybe 200 nanometers. So we really use this as absorber, and this is as a readout, JJ. Yeah. Yeah, those are all like niobium or niobium nitride superconductor leads. Right. So, and I mean, I'm probably going to stop here. So we of course also try to see what the mechanism is of this JJ. Is this really heating? Then we had a lot of temperature-dependent studies of all of those characteristics. But I think I'll probably stop there. And yeah, so I think like I think we did a good step forward to make this type of devices, whether it's ever going to be something useful, whether, you know, I mean, of course, their motivation was to get a single photon detector in the terahertz, where there is no competing technology. There is no single photon detector in the terahertz range. So whether this is going to be something, you know, applicable, we will have to see, I guess. For sure, if you go to the terahertz, you need to have a different principle. You need antennas coupled to it. But yeah. So yeah, here's the switching rate. Oh, this was, yeah, so we tried different light sources. So we did, of course, sorry? Oh, for this one we didn't use a cavity. So my cavity was, for the previous results, the cavity was at 1550, so telecom, 1550 nanometer. For this one, we particularly tried to go to longer wavelengths. So for this one, sorry? There's no cavity, just without any cavity, yeah, exactly. So I think we, right now, with the single photon detector, we just want to show that it works. And then we will try to make it more efficient to couple it to an antenna or a cavity or. Sorry?
Sorry, I think it's extremely useful.
Yeah. Okay.
Who I can sell it to, like, I'm asking the question.
So this particular data was done in also the telecom link, so 1550 nanometers. The longest wavelength we tried, we had a laser at one point with 8 micrometer wavelength, so approaching the DR.
That's good.
But
I just want to know how many zeros behind the one.
okay. So, but yeah. So our guess is that. So actually, oh, sorry. I'm sorry. So our collaborator Casey Fong, he's actually doing this also on a superconducting circuit platform as well. So there you have gigahertz frequency photons. So this is like those photons will run through the superconducting transmission lines, right? So he also sees similar stuff there. So we didn't go to the terahertz, we went all the way to the gigahertz. Yes. Yes. So yeah, so basically the same device, but coupled to like a superconducting circuit cavity. So to like lambda half plate resonator. As far as I know, yes. So this is also some stuff which I'm not directly involved with. So this is more work of. So I have no data to show that right now. Yeah. So basically. Yeah, so I think like power dependence. So once you get high enough power, you start absorbing more than one photon at a time, or there is a probability that you start absorbing more than one photon at a time. And if we go to really high powers, then we see that it deviates from a linear fit, so it becomes nonlinear. So and there probably 2 or 3 or more photon events start happening. Oh, so yeah, I don't know. Like, I mean, see, like, if I mean, if
Is it the photon number resolved single photon source? I think is what Ketchen was asking. Distinguish between 2 photons arriving at the same time or 1 photon?
This is at this point, no. With this measurement readout, with this threshold measurement readout, we don't. Oh, so that's what I said, that we did all this more temperature-dependent studies as well to figure out the real mechanism. So we have that. I can show you afterwards if you want. Yeah. So yeah, of course, I mean, this whole, all the details change as a function of temperature, et cetera. Okay, so I mean, so I didn't want to go into the details, but yeah, so we do this type of experiments where we try to distinguish 1 versus 2 photons, et cetera. Yeah, so we try to do that. This story is not conclusive enough yet that I can make a strong claim right now. But as you see, like we try to do to estimate how much energy is 1 photon, 2 photons, and then we try to see at the switching currents and the statistics there too. Okay. Yeah. Oh, it's very small. It's very small. Yeah. So yeah. So basically, yeah. It's what is that? It's micro electron volts, something like that. I think. What's that? Is it
10 gigahertz is about 10 microvolts.
yeah. Yeah.
Yeah, which is about.
Yeah.
But that's absorbed, that's for 1 photon, but now you have a graphene sheet with millions of electrons in it or something.
Yeah.
Not so many, actually. Not so many. So
I mean,
a few electrons per second.
yeah, yeah. I mean, yeah. So they're definitely those energies already come to the limits of this whole story, and of course you would expect also a huge dark count to compare. You know, you would probably you would expect a huge dark count, so you would expect a lot of clicks due to other mechanisms that just that. So that story will, I mean, yeah.
I mean, but in principle, theoretically you have sensitivity. I don't know in practice how it works.
Right.
With the numbers that you gave us for the temperature increase for the visible photon.
Yeah. Yeah. So that's the number. So.
Few gigahertz photons, you're there.
Yeah.
In a millikelvin.
Right. You would be like in sub-millikelvin temperature increases. Yeah. So for like again for like picoseconds to nanoseconds depending on the temperature. Right. That's right.
Okay, there are no more questions. Let's start.
All right. Thanks.